Now let's consider the case when elimination in the matrix AX equals B gives us columns that gives us only pivot columns. Such an example is the matrix A. How do we know, without carrying out any elimination, that the matrix A has two columns that are pivot columns? Well, it's simple. A free column would be a linear combination of the pivot columns. So if these two columns, since these two columns are not multiples of each other, we know that both of them will have pivots after elimination is carried out. So because the matrix A has linearly independent columns, we know that AX equal to 0 has only one solution. So let me write that. Since A has full column rank, that is, it only has pivot columns. The null space of A, so since this, the null space of A is the set that contains only the 0 vector, or the only solution to AX equals 0 is X equals 0. And that's what it means to have a 0, to have the null space only be 0. So in this case, the complete solution really consists of one particular solution. So we don't have infinitely many solutions, because the infinitely many solutions really come from a non-zero null space. Since the null space is 0 in a full column rank situation, we're only going to have the two cases. Either AX equals to B has a unique solution, or AX equals B has no solutions. So in this particular situation, it makes sense to ask for which B's does AX equal to B have A, and we know if there is a solution, it will be unique. I don't have to state the fact that the solution will be unique. It's just more of a reminder that I put it there. But it would be a unique solution because uniqueness has to do with a 0 null space. If you don't have a 0 null space, then one solution means infinitely many solutions. Now, why does B have to satisfy any rules? Why is it that there can be vectors B for which AX equals to B does not have a solution? The reason is that the vectors B that we are considering, which are linear combinations of the columns of A, are vectors with 3 components, but since there are only 2 columns, we know that the column space of A is a plane and not the entire 3D space. So if you take a vector B, which is not a linear combination of those 2 vectors, and we can take many such vectors, then we would not have a solution. So we've seen this problem done over and over again. We had it on the test, so nothing new, but let's just review more than anything. So we can augment the vector B with general B1, B2, B3 to the matrix A. Here is B1, B2, B3, and we will carry out elimination in A so as to get to the matrix R, to the row echelon form of A. So I will eliminate under the first pivot. The operations in question are R2 minus R1 into R2, and R3 plus 2R1 into R3. the result is 1, 1, B1, then 0, 1, B2 minus B1, then 0, negative 1, B3 plus 2B1. And then the next step in getting the reduced row echelon form is to take the second pivot and eliminate both above and below it, so two operations. So we're going to have R1 minus R2 into R1, and R3 plus R2 into R3. So now I'm changing the first row. Here I will have 1, 0, and then I will have B1 minus B2 minus B1. So you see it will be B1, maybe I'll just write it here and then I'll delete it just to take this slow. B1 minus B2 minus B1. When you open parentheses, you get B1 minus B2 plus B1. So really, we have 2B1 minus B2. So here I have 2B1 minus B2. The second row stays the same. That's B2 minus B1. And then the third row becomes 0, 0. And I'll do the calculations on this side again. I have B3 plus 2B1 plus B2 minus B1. So this negative B1 and that 2 essentially cancel out, and we have, well, really B1 plus B2 plus B3. Now I'll remove the side calculations to make some room. So how to answer the question? You see, if I want this new, so remember, we started with A, B here. We carried out some elimination steps. And we got to an equivalent, but not the same system, of R, D, right? What we have on the right-hand side is the vector D. And because A has full column rank, R is sort of an incomplete identity matrix. It only consists of columns of the identity matrix. And you see, you can always express the vector D as a combination of the columns of R, provided that the last component is 0. That is the only condition. Doesn't matter what this is, doesn't matter what this is, because you can always say, well, this number times 1, 0, 0 plus this number times 0, 1, 0 is going to give me the vector that has this component, that component, as long as this is 0. So the condition comes from that 0 row. So condition on B is that the sum of its components must be 0. And if that is the case, so if B satisfies this condition, so under those conditions, the solution, the general solution to the system would be, so think of this part as not being there, so don't worry about it. You're trying to express D as a combination of the columns of R, but that's very easy. So that is 2B2 minus B2 times 1, 0, 0 plus B2 minus B1 times 0, 1, 0. So the sum that you get there really is just the solution, which essentially means that the solution is the vector D in this particular case. So, sorry, it's not the vector D, but rather the first two components of the vector D. So you're, I think I made a mistake here. I said that wrong. So it is true that this is what D is, but that means that this is x1 and this is x2. So the solution to the system is x containing 2b2 minus, 2b1, this should be a 1, minus b2, and then b2 minus b1. So this is unique because b1 and b2 are whatever they are. And we have that solution for a system when A has a full column rank.